And so once the baseline impeller is ready, a CFD analysis is run to check the actual performance. And for this, we use ANSYS TurboGrid for the fully structured grid of a single passage and CFX for the flow analysis. And here are the different CFD settings where these boundary conditions are chosen to match the inlet and outlet conditions in Turbo Design Pre. And also a large tip clearance relative to the blade exit width is used, which is commonly observed in these compressors. And in fact, the CAE integration feature is used, which provides a direct link between your blade designs in Turbo Design 1 and their CFD analysis on commercial software. So all you need to do is add a CFD connection, and then in this window you specify which case you want to run CFD on, after which you have the option to choose between ANSYS CFX and Star CCM Plus, and then provide some other CFD settings such as wall plus value, turbulence model, and number of iterations. And you can even run multiple points with different flow rates around the design point. For example, here we want to do extra runs at plus minus 10% of the design flow rate to verify the throat area. And then once you kick off the CFD runs, the mesh is automatically created in TurboGrid, and then the CFX solver starts running. And when CFD runs are complete, what we find is that the peak efficiency happens at the design flow, meaning that the impeller throat is correctly sized for the design condition. And so let's have a look at some other results from the baseline CFD at design point. And here we have these velocity vector plots in the blade to blade view, which are showing the influence of the large relative tip gap even at 80% of the blade span, but the flow behavior is otherwise good inside the impeller.